So how many protons with a pKa of less than 22 exist in this molecule? Well, let's just go ahead and look. Alcohols have pKa's of about 16, so the alcohol is going to be 1. Then ketones have alpha carbons that are at about 19, between 16 and 19. So let's look at them. How many alpha carbons here? 1. How many there? 2. So the total is 4, and that is the correct answer. Which of the above carbonyl compounds is most acidic? Well, right here we're looking at alpha carbons having protons. So here, this is a ketone with a pKa of about 16 to 19. This is a ketone, but individually these are both going to be probably a little bit less than 16, but not much. Here, this is just normal ketone again, maybe a slightly less than just cyclohexanone. But here we have two ketones that are both alpha to this carbon right here. So we have one that is very acidic. C is most acidic. Rank these from least to most acidic. Well, the most acidic one here, of course, has to be the carboxylic acid. So that's going to be either 2, 3, or 4. Most acidic, sorry, 1 or 2. All right, so then next most acidic would be, of course, one of these dicarbonyl compounds. Ketones are more acidic than esters, so I'm going to say A is next. That would give us this. Then B is one ketone and the other is an ester, so that would be next. And then C is diester. So 5 is going to be the correct answer. The equilibrium will favor the products in the following reaction. Well, this looks like an unusual compound, but that's a keto form of phenol. So will this reaction go to the right, or will it stay in the keto form? Well, it will enolize and form phenol. Then is phenol going to be deprotonated by sodium hydroxide? We've learned that a long time ago that phenol is easily deprotonated by sodium hydroxide. It's a strong enough base. So true. The products are favored in this equilibrium. So what is the product of this series of reactions? Well, let's look at the reagents and the products. We have a dicarbonyl. Actually, this would be called a beta ester, beta keto ester. What are we doing? We have sodium hydroxide. What would that do to an ester? That would hydrolyze it and make it into a carboxylic acid, actually to the acid salt. This would then protonate the acid, and then if we heated this, we would have decarboxylation. So if I didn't have heat, the acid would be formed. If I look at the rest of this, there is no way that a phenyl will be cleaved off from here. That carbon-carbon bond is not going to be broken, so this wouldn't happen. Right here, there's no way that this is going to come off this compound, so that's not going to be the product. Neither is this. This is going to be the product because what's going to happen is this is going to cleave, form the acid, and then heat is going to cause decarboxylation. So this is the correct product. What is the product of heat in this reaction? Well, if I look at this, you might think you're going to have two decarboxylations. But you can see that this and this are only beta. This is gamma, away from either of these carbonyls. So only one of these is going to be lost. And what are you going to end up making? A ketone, methylene, and then a carboxylic acid. So this should be the product. So what is a product of this series of reactions? Okay, if I look at this, I've got my malonic ester here. Treating it with sodium ethoxide is going to deprotonate this, and then we're going to do SN2 on one end of this alkyl halide. Then treatment with sodium ethoxide would cause deprotonation and attack at the other end. Treatment with sodium hydroxide would cleave off the esters. Treatment with acid would protonate, and then heat would decarboxylate. So what would we end up with? One of these gone, this being an acid group, and then 1, 2, 3, 4 carbons attached to here. And that would be this compound right here. Can an acetoacetic ester synthesis be used to make this compound? Well, when we're looking at an acetoacetic ester synthesis, we look at for a part of a compound that looks like acetone. So I see right here is what looks like acetone. That was the carbon that was between the carbonyls, and then on the other side was a carboxylate, an acid group. So could this have been made? Well, yes, because this could have been benzyl chloride or benzyl bromide, and this could have been benzyl bromide, and then we could have heated an acid and decarboxylated. So true, this could have come from an acetoacetic ester synthesis. Which of the following cannot be prepared by the malonic ester synthesis? Well, in the malonic ester synthesis, what we look at for is something that looks like acetic acid. So right here, that looks like acetic acid. And there is an alkyl group we would use and an alkyl group that we would use. So that could be made. We've got that acetic acid here, and then we could have an ethyl bromide and an allyl chloride or whatever. Right here, this is the acetic acid portion, and this could be a halogen here and a halogen here, so like 1,5-dibromopentane. And here's my acetic acid here. That could be a benzyl bromide, and this could be an ethyl bromide. And here, this is my acetic acid, and this could be like a methyl bromide, and well, that would have to be a vinyl halogen halide. They won't do SN2. So this one can't be made with an SN2 on this carbon, so it cannot be from the malonic ester synthesis.